Hello students, in the previous lectures we have derived the equation for gradient of a scalar point function, divergence of a vector function, curl of a vector function, and equation for Laplacian operator in curvilinear coordinates as well as in Cartesian coordinates. Now we'll have a special type of curvilinear coordinates, cylindrical polar coordinate. We'll derive the equation for the unit vectors as well as for the surfaces and the curves in cylindrical polar coordinate, and then drive the equation for curl, gradient, divergence, curl, and Laplacian operator in the cylindrical coordinates, in comparison with the equation of the gradient, curl, divergence, and Laplacian operator in the curvature coordinates. So let's drive equation for the gradient, curl, divergence, and Laplacian operator in the cylindrical polar coordinates. So let P is any point in three-dimensional space, in Cartesian uh, space. P is a point, any point in the space, Cartesian space, uh, whose position vector is given by r is equal to x iota plus yj plus zk. X iota plus yj plus zk into this. This is diagram. Now this is the diagram form. This is x-axis, this is y-axis, and this is z-axis. Z-axis, x-axis, y-axis. Now it's a point. We point in the space. And now let rho, phi, and z respectively denotes the projection of projection OM of OP. Projection OM, this OM of OP. OP, this on x-y plane. X-y plane, and the angle which OM makes with the x-axis, and angle with the x-axis and perpendicular MP on x-y plane. Perpendicular on x-y plane. So these are, this angle is phi angle and phi angle. Phi angle which makes with the x-axis and perpendicular MP on the x-y plane. Then the cylindrical coordinates of the point P. In order to reach point P in Cartesian plane, we move this parallel x-axis, then y coordinate, then z coordinate in the Cartesian coordinate. Now, in order to reach this point, we move in the similar manner, but the projection of this will be rho is this, and this is rho theta phi respectively denotes the projection. This is rho, projection OM of OP. This is rho, and phi is the angle which this projection make with the positive direction of x-axis. Positive direction of x-axis. Positive direction of x-axis. This formula. This is rho. This is a phi, and z is the perpendicular distance. This perpendicular and therefore the Cartesian coordinate of the point P were x, y, z. Now the cylindrical coordinate of this point P are rho, phi, and z. Rho is this angle, phi is this OM, and z is this. So in order to reach this point in cylindrical coordinate, we have to move that axis this along x-axis. We move along x-axis. This is long axis. This is the projection from here. This is the projection from this L. This is point L, and this is 90. This is 90. This is 90. Right? So that now the surfaces. Now x, y, z were the coordinate. Let's so now the spherical coordinate. Now the curvilinear coordinates of the point P means the spherical coordinate. In the curvilinear coordinates we have u1, u2, u3 are the independent variables which were independent partially counted differentiable. Now in cylindrical, in this is cylindrical coordinate, U1 will be rho, U2 will be phi, and U3 will be equal to Z. U3 is equal to Z. If we take this, consider this triangle, that is triangle OML. OML, this is X, this is X, this is Y. Uh, OL upon OM, base upon hypotenuse, is equal to cos of phi. Is phi. Similarly, OL is equal to how much? OL is equal to X, which is equal to rho cos phi. Similarly, ML upon OP is equal to perpendicular over hypotenuse is equal to sine of phi. Therefore, ML is equal to rho sine phi. Y is equal to rho sine phi. And Z is same. Z is equal to Z. So these are this relation between the cylindrical and particle. That is the important of the point. So the Cartesian coordinate are fixed, but the cylindrical coordinate varies from point to point. As we know that the curvilinear coordinates, unit curvilinear coordinates vary from point to point, and direction vary from point to point. Similar case, because they will behave as curvilinear coordinates. Now we we have we have what is we have x is equal to how much? X is equal to rho cos phi, y is equal to rho sin phi, and z is equal to z. Now, what is rho? Rho is from rho in this section. So rho is this. Rho is from 0 to infinity. And phi varies along in x plane. This take one complete rotation means phi varies from 0 to 2 pi. And z is from minus infinity to this is center. This will be the center. These are the coordinates. This is the relation between the Cartesian polar spherical cylindrical coordinates. Now let's convert the x y z find the equation to the surfaces in the this cylindrical coordinates. We'll solve the equation for rho, phi, and z. Squaring adding first and second, x square is equal to rho square, is equal to rho square, and rho is equal to 1 root of x square. And similarly, y upon x is equal to tan inverse of phi, and z is equal to. So from this, phi is equal to tan inverse of y upon x and z is equal to. Now these three equations, equal to this, phi this, z this. Therefore, the coordinate surfaces are given by these are the coordinate surfaces. Rho is equal to constant and rho is equal to constant. These are coordinate surfaces. X, Y, Z earlier coordinate surfaces and Cartesian coordinate, we have converted them to coordinate surfaces in cylindrical polar coordinates. So rho is equal to constant means that is x square by y square is equal to c is equal to x y square is equal to c1 square c1 square. This surface is cylinder coaxial with z axis. Axis will be parallel to axis. Now phi is equal to c2. This phi is equal to tan inverse of y upon x equal to c2. Therefore, y upon x equal to tan of c. Y is equal to tan c 2 of x. This is the surface. This surface is a plane through z axis. Surface is a plane through z axis. This is plane. This plane. O M P N. Well, this will rotate. Rotate the point. This will rotate. This is a plane value. This will rotate the point from the whole space. Now, the next question is then z equal to c3. This surface is a plane perpendicular to the axis. Z equal to c2, z equal to c2. There is plane perpendicular to the perpendicular to this. Perpendicular to this is z axis. Let me see. This plane. This plane. Now these are the three surfaces. These surfaces. The point P is the point of intersection of these three surfaces. So what the coordinate point P is the point of intersection of these surfaces. Is equal to x square plus y square equal to c1 square, y is equal to tangent c 2x, and z equal to j. The point of intersection of these surfaces. And the coordinate curves for rho, y, and z are respectively straight lines perpendicular to z axis. Z axis, horizontal circle with center on z axis. The point P is the point of intersection of these surfaces, and the coordinate curves for rho, phi, and z are respectively straight lines perpendicular to z axis. Number one, horizontal circle with center on z axis and line parallel to z axis. These are the coordinate curves. So these are the coordinate surfaces and the coordinate curves. So coordinates are given to us. Now let the unit vectors where e1, e2, e3 be denoted by let the unit vector e1, e2, e3 be denoted by e rho 1, e rho 1, e5, e rho unit vector, e5 unit vector, e z unit vector, respectively in the cylindrical coordinate system. These are the unit vector. E1, E2, E3 are the unit vector, tangential unit vector. So in the cylindrical coordinates, E rho vector, E5 vector, Ez vector, strictly are the strictly in cylindrical coordinate system are the unit vectors. Then E rho unit vector acts along NP. I show the figure. This acts along NP. This acts along NP. NP. This all and E5 act perpendicular to the plane ONPM in the direction of phi increasing, and EZ act vertically upwards in the upward in the direction of increasing z. So now we are three vectors at this point. E rho will act in this direction, E5 in this direction, the theta increasing, and EZ in the direction. So this will behave as a right hand. This will form a E rho, E5, E and EZ make a right handed system here at this point. And we know that in cylindrical coordinate it varies from point to point, direction of it varies from point to point. Now prove the cylindrical coordinate system are orthogonal. Now we prove that these coordinates are orthogonal. We try to question for them and we prove that they are orthogonal. Orthogonal let are the question to point. So in cardinal coordinate is equal to r vector is equal to x hat over y z k, and in it will be if you convert into the cylindrical coordinate, this vector point will become rho cos phi iota rho sin phi of j and z. Now we'll find a tangent vector in the root tangent vector to the curve rho curve at P. Tangent vector to the rho curve at P. That is phi and z will remain constant. So partial derivative of this r vector, which is in the cylindrical coordinates, is 2 rho. That will be partial rho r vector is 2 rho. You can see this. So cos phi iota sin phi j and this is equal to rho. Now what will be x for that? Because even if equal to this is tangential. Now we are already find tangential unit vector. So tangential vector is equal to vector upon magnitude of the vector. So this is tangential vector in the direction of rho increasing. Increasing is equal to x compared to now. So E1 vector or this is equal to E rho vector. E rho vector will be equal to partial derivative this R vector is to rho upon its conjugate. Equal to, so E1 vector comes out to be cos phi rho plus sin phi cos phi iota plus sin phi vector. Similarly, we can find E phi vector, E z vector are unit vectors to phi curve and z curve at point P respectively. So E phi comes out to be positive R vectors to phi upon its conjugate. So to positive R vectors to phi this could minus sin phi. So rho this will be how much? This rho minus rho sin phi iota is equal to rho cos phi j, and the modulus of this will be equal to rho when we discuss definition of this is this divided by h upon h. This comes out to minus rho sin phi e iota plus cos phi j, and each vector is equal to e z is equal to partiality of r vector in the cylindrical coordinate with z upon this function. So z equal to k and u is equal to 1. So it's made the same. Now, in order to show we have calculated the unit tangential vector along the rho curve, phi curve, and z curve. We have calculated the unit vector along the rho curve, tangent to the rho curve, uh, tangent to the phi curve, and tangent to the z curve. Now we'll show that they are orthogonal. So find the dot product. E rho dot E phi comes out to be E rho dot phi is equal to 0. Similarly, E phi dot E z is equal to 0. E z E rho is equal to 0. And this implies E rho, E phi in E z are mutually perpendicular, and hence cylindrical coordinates are orthogonal. Cylindrical coordinates are orthogonal terminal coordinates. Perpendicular, hence cylindrical coordinates are orthogonal terminal coordinates. Now, if you to check for the cross product, E rho cross E phi, this comes out to be E z, like the product, same I j k. I cross j is equal to k. So E rho E phi is equal to E z. And similarly, you can check for E phi E z is equal to E rho E z E rho is equal to E phi, and the magnitude is equal to E rho magnitude is equal to 1, E phi magnitude is equal to 1, and E z is equal to 1 magnitude is equal to 1. So they come out to 1. So they behave, hence E rho vector, E phi vector, and E z vector form a orthogonal right-handed basis. Also right-handed basis. Now relations between these bases. Relationship between Relationship between cylindrical and Cartesian bases. So we have tried the equation. E rho is equal to, in terms of Cartesian, E rho is equal to cos phi iota plus sin phi j plus 0. E phi vector is equal to minus cosine phi iota plus cos phi j plus 0. E z vector is equal to 0 iota by 0 0 0 k. Now, if you convert them to matrix form, A E is equal to Q, P is equal to A cross P. Now, if you multiply both sides by E inverse, this convert A inverse into A, because E vectors are linearly independent, so their determinant comes out to 0. Independent. So inverse is equal to Q is equal to A, I into Q is equal to Q is equal to A. So if you find the inverse of the A, is of A, substitute value ij comes out to be E inverse into so P. So with the help of this, we can convert from cylindrical to part. So we can find ij in terms of cylindrical coordinates. Now, if you are asked to derive the equation of our gradient of phi in this cylindrical coordinate, you straightway substitute the value of E1, E1, H1, E2, H2, and E3, H3. E1 is equal to 0, E2 is equal to E5, and Ez is equal to E3 equal to Ez, and H1 is their magnitude, and you get the equation in the this cylindrical. This is the equation for curvature coordinates in the curvature coordinates for the gradient of phi. Now you can find the equation if you replace the values E1 by E1 by its value, E1 by E rho, E2 by E5, and Ez by E3 by Ez, and H1 is the modulus. So to the values, you will get the equation in this for gradient, for divergence, for curve, as well as for the in the cylindrical